Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, so today's lesson 3.2.2, we are going to deal with some different equations where there isn't always going to be just one solution. We've already seen some situations of this, but let's go back over it and work through the process of solving these equations. They're going to be a little bit more complex. And of course, we always want to check the solutions. And I'll show you kind of a shortcut way of checking the solution. I'm not always asking you to write out extensively every single thought that comes into your head as you're working through a problem. There are shortcuts that you can make while still ensuring that you're getting the answer correct and working through all the steps. So let's get to it. In lesson 3.2.1, you reviewed your equation solving skills to remember how to find a solution to an equation. But do all equations have a solution? And how can you tell if an equation does not have a solution? Today, you will continue to practice solving equations and will continue to investigate the meaning of a solution. Okay, but first, let's play a game. This is a type of game. It's called Guess My Number, where you have to use some reverse thinking or some algebraic thinking. And so this is kind of like, how word problems we saw with the 5D process last year, where there were a number of different strategies you could use, but most students were getting really good at defining the variable, setting up an equation, and solving the equation. Well, anytime you've got an unknown embedded into a situation with some known quantities, you can generally use reverse thinking and algebraic thinking to figure out what that unknown quantity is. So I'm going to go ahead and do each one of these one at a time. Let me get my favorite color. Very nice. Don't ask me why that's my favorite color. I just like it better than the other options. Okay, so this is what I would like for you to do. I would like for you to copy down this statement. When I triple my number and add 4, I get 10. Now, as we're going through and solving these problems, let me skip forward to the next page. Generally, it's a good idea to start by writing an equation. And then solve that equation, going through each one of the steps, and then go back and declare what your answer is. Okay, so what would the equation be for this particular situation? What is your variable? Okay, so let's analyze this. When I triple my number, we don't know what the number is, right? That's what we're trying to figure out. So your number is going to be the variable, and you're going to triple it. What does it mean to triple a number? It means to multiply it times 3, correct? And add 4. So which one of these has to happen first? The multiplication of 3 or the addition of the number 4? This is where order of operations comes into play. When you're thinking about what you would do first, what would you do after that, and what do you get as a result. So this I get portion right here is kind of a word way of saying is equal to. Okay, so my number times 3 plus 4 is going to be equal to 10. So if you wrote down this as your equation, that would be correct. Okay, so now let's use some reverse thinking and algebraic thinking. We could go through and we could solve it by adding or removing balanced sets and then dividing by a number. But I want you to think about this in a slightly different way, because the more different ways you can think about how algebra works, the more it makes sense in the long run. Okay, so let's just consider this for a second. I'll use my highlighter and maybe I'll highlight in green. You see this quantity right there? We don't know what x is, so we don't know what 3 times x is. But we do know that when you add the 4 to this quantity, you get 10. So let's just think about that quantity. What does that quantity have to be? What do you add to the number 4 to give you 10 for an answer? And if you said that would be 6, then I would say yes, absolutely. So after subtracting 4 from each side, you should see that 3x's is equal to 6. So what does your number have to be then? What do you multiply times 3 in order to get 6 for an answer? Well, remember our last step when solving equations would be to divide, and you divide 6 by 3, correct? If 3 times a number equals 6, then 6 divided by 3 will tell you what that number is. So what is that number? What's your mystery number? It's got to be the number 2, right? So this eventually becomes x is equal to 2. So I want you to think about these equations logically, not just try and memorize a series of steps and a series of processes. I want it to make sense why we're doing what we're doing. That's the key to middle school math. And once you understand why we're doing what we're doing, then you'll be able to apply it and everything will make sense and you'll remember things. And that'll better prepare you for high school when things get really, really complicated and abstract. Being able to just focus on why something works rather than memorizing a process is going to help you tremendously with your understanding of concepts, with new concepts in math. All right, so let's see if you can do this one on your own. This one's a little bit more complicated. It says, when I double my number and add 4, I get my number plus 7. Okay, so what is your variable? Your variable, once again, is your number that we don't know. So you're going to double the number, add 4, then you're going to get, remember that I get was the same as the equal sign, my number plus 7. So go ahead and write down that equation and see if you can figure out what the solution is. Okay, I'm going to go ahead and pause. You go ahead and pause. And if it's it's a little more complicated than game 1, so you might want to make a few adjustments before you start thinking about it the way that we thought about game 1. Go ahead and take a little time with that. All right, so let's see. Did you get the equation? What is that? When I double my number, so that would be 2x, and add 4, 2x plus 4 would be equal to x plus 7. And let's see, just using a little bit of algebraic thinking, we've got x's on both sides. So if I take away this x, I have to remove one of those x's. So that becomes x plus 4 is now equal to 7. So now you can clearly see what your number is going to be, right? Just making that one little step. You're going to give me my highlighter? There you go. Just by giving me that one little step there, you can see that x is going to have to be equal to 3, since 3 plus 4 is equal to 7. Okay? Now, in a situation like this, it'd probably be good to check it just to make sure and do a little mental check. If you know that x is equal to 3, then this should be equal to 6, right? 2 times 3 is 6, and 6 plus 4 is 10. So does this side equal 10 when you plug in the 3 for the x? 3 plus 7 is 10? Yeah. Both sides are the same. They're both equal to 10, or they're both 10s. And that's the proof that your solution for x was correct. All right, let's look at the last one. When I double my number, oh, no, I want to color code it, right? There we go. When I double my number, remember that means to multiply times 2, and add 3, then I subtract my number and subtract 1, I get my number plus 2. That's an interesting one. So we're going to double the number and add 3. And you're going to subtract your number, and then you're going to subtract 1. You're going to get your number plus 2. All right. Now, this is one where we're absolutely not going to be able to just go through and do the mental processes very easily. So this is one where you absolutely should work through the process just a little bit. I'll change my color here. So let's combine the like terms. The 2x's and the negative x make 1x, and the 3 and the negative 1 make 2. So now you've got it rewritten in simpler form where x plus 2 is equal to x plus 2. If you take away the x from each side, you'll notice it says 2 is equal to 2. Now remember, when we eliminate all of our variables and you're left with a true statement, that means that the answer is all real numbers work as solutions, right? So can you identify what the solution is? No, because there are an infinite number of solutions, right? Think about it this way. I'm going to go ahead and erase this. If you just think of it this way, this quantity is exactly the same as that quantity. If x is equal to 1, then it has to be equal to 1 here, and you get 3 is equal to 3. That's a true statement, which means x would be equal to 1. But if you put x is equal to 2 and x is equal to 2 here, then 2 and 2 make 4. So 4 equals 4. That's also a true statement. So this kind of a problem that we have right here for game number 3 is one of the reasons why doing the guess and check process with the table that we did in the 5D process is not an ideal way to solve algebraic equations, because the first one that you check here and plug in would work, and you'd say, oh, I started with 1, so x has to be equal to 1. And then someone else in your table group said, no, I started with 2, and x is equal to 2, and that worked. And then you start having an argument about which one is correct. Well, it turns out in this situation, we would say that all numbers are correct. There are an infinite number of numbers that would work. Every positive number, every negative number, every fraction or decimal number would work in this particular equation as a solution. Okay, so in today's work that we're going to do, which, how much time do we have? Okay, this is going to be a quicker lesson. We've just got 6 problems that I want you to copy down. Let's go ahead and go to problem number 81. Copy down each one of these questions and solve each one of them. Go ahead and record your steps and then check your solution if possible. Now, in a situation like this, you can check your solution pretty easily. You just plug the numbers into the original equation and prove that it's correct. But if you've got all numbers, then it's kind of hard to check it, right? Other than like choosing 2 different numbers to prove that both of them work, or 3 different numbers to prove that each one of them work. If there's no solution, which that's a possibility, right? Then you can't check anything, right? I mean, you could check, but nothing will work. So there's really no point in checking if there's no solution. So go ahead and take your time, copy down each one of these problems, then I will do the reveal and I will show the work and show the process for each one of those. Okay, go ahead and pause, and when you feel like you've got an answer for each one of them and you've checked the ones that can be checked, and unpause, and I will show you the work that I've got for each one of those problems. So in case you made a mistake, you can fix your mistakes. All right, let's take a look at problem A. So for problem A, we copy the problem down as is. Then it looks like we need to combine like terms on the right-hand side. So x and 3x combine to make 4x. And notice how you've got the same situation that we had on the previous problem for game 3. This expression is exactly the same as this expression. So whatever number you plug in for x here, you plug the same number in there, and you're going to get the same answer. So no matter what you put in there, all of these numbers are going to be correct. So you can plug in a number of different numbers. I like to check, like when it's something like this, use the number 0, because you know that this is going to be a 0, this is going to be a 0, and that's going to be a 0, right? Because 4 times 0 is 0, and 3 times 0 is 0. So you get -5 is equal to -5. Yes, that is correct. So 0 works. Now let's plug in the number 1. 4 times 1 is 4, so this becomes 4 minus 5 is equal to -1, correct? And here you're going to have a 1 there and a 3 there and a -5 here. So you end up with -4 plus 3 is also -1. So here I've checked 2 different solutions and both of them worked, which means I'm correct. All real numbers are solutions to this equation. Looking at B, we start out with the equation, and now you need to combine like terms negative x and negative 4x with negative 5x. And now I would work through the process. I generally like to collect the x's on the side where you've got a greater coefficient. Remember, the negative 5 is a coefficient, the negative 2 is a coefficient. If I add 2 x's to each side, I'm going to have a negative 3 x's on this side. If I add 5 x's to each side, I'm going to have a positive 3 x's on this side, and I would rather have the positive 3 x's on this side, so I choose to add 5 x's to each side. Now that my 3 x's are here, I'm going to have to take away 5 from each side, which means I would add a negative 5 to the negative 7, and you end up with 3 x's is equal to negative 12, so x equals negative 4. So if that is our solution, we should be able to plug those numbers in here, and the left side will equal the right side. So here's my little shortcut, kind of a, I'll do this in green, and I'll do it with a roll thin pen. So this means the opposite of negative 4, so that would be a positive 4. And then 4 times negative 4 is negative 16. So we're going to subtract negative 16, which means that's the same as adding a positive 16 minus 7. So 20 minus 7 gives me 13 on the left-hand side. Here, we're going to take negative 2 times negative 4, which is positive 8, and positive 8 plus 5 is equal to 13. 13 is equal to 13. This is my check. It's not a real official, formal kind of a check, but it works, okay? So it's almost like a mental check, although in this case I couldn't really do it mentally. But you kind of get the idea that it doesn't have to be a big, complicated process for you to check your work. This proved that x was equal to negative 4, so I'm going to declare my answer. For problem C, copy down the problem, then combine like terms. It looks like I've got 5 x's and negative 7 x's, make negative 2 x's, and 3 and negative 4 make negative 1. And here, you end up with negative 2 x's plus 1. Well, after taking or adding 2 x's to each side, you end up with a statement that's not even true. Negative 1 doesn't equal positive 1. So I'm going to go ahead and put a little slash in there saying, no, that does not work. There's no solution for this particular one, and I'm not going to check it because I don't expect anything to work. Okay? For problem D, copy down the problem. Use distributive property to rewrite this as 4x plus 3x minus 2. So 4x's plus 3x's is 7x's, and here you've got, just like with problem A, in game 3, this expression is exactly the same as that expression. So we're going to end up with all real numbers work. So go ahead, you could check multiple, oh no, that's this one right here. You could check multiple different numbers and they will always work. Let's start with number 0. That would be 0. This would be 0. And so when you send in the dive bombers, you end up with the negative 2 on the left side. And if 7 times 0 is 0, 0 minus 2 is equal to negative 2, which makes the left side equal to the right side. I guarantee you, any number you check in there is going to work. Go ahead and feel free to do that, but I feel confident our answer is correct. Now for E. This one has a little bit of distributive property that we're going to have to work into it. Sending in the dive bombers there. Combine like terms on the left-hand side, that becomes 2x's plus 6. On the right side, that becomes a negative x and negative 4. The negative x combines with the 3x to make 2x's, and the negative 4 combines with the negative 2 to make negative 6. This problem is similar to that problem. 2x plus 6 cannot be equal to 2x minus 6. There's no way that that would work. So we are going to say, since these two are not equal to each other, that there's no solution. And then for F, copy down the problem, send in the dive bombers here to make this x minus 5 minus a 2 plus an x. So and then the x and the x makes 2x's, and the -5 minus 2 is the same as -5 plus a -2, so that's -7. Now, one thing to be aware of. Once you notice that you have a different number of x's on each side of the equation, like we did here, once you realize that you can collect all of your x's on one side of the equation, like we're seeing here and here, you will always have a single solution. The only time you're going to have all real numbers or solutions or no solution is when you've got the same number of x's on each side after going through the simplification process. So that's your clue. There'll always be one solution if you can get your x's alone on one side of the equation. If you can't, there will either be no solution or all numbers are solutions. So in this case, I know there's going to be a solution. It's just a matter of figuring out what that solution is, and then we'll check it. Let's add 7 to each side. 7 plus -3 is 4, and 2 times 2 is 4, which means that our solution has to be 2. So let's go ahead and check that to make sure that our solution is indeed equal to 2. So this becomes 2 minus 5, and then 2 minus 2 is 0, right? So minus 0, so 2 minus 5 is -3. That's what it's supposed to be equal to. That proves that our answer is correct. So we will declare, I forgot to do my reveal over here, no solution, and that means that our solution is 2. Okay, so the more you practice this, the better you get, okay? You've had practice in 7th grade. The examples are getting more complicated. Notice all these negatives where you'd want to do KFC and do distributive property in some of these instances. In the next few lessons, we'll be adding in decimal and fractions. And you're going to be allowed to use your calculator to help you along the way, but I will also teach you strategies on how to deal with those fractions and decimals. But we've got to get the processes down. We've got to know what it means to have all numbers be solutions and have nothing be a solution. And we also want to be able to recognize when there is going to be a single solution and how to check that, okay? So get to your homework, do the best that you can, show your work, and once again, if you make mistakes, we can fix them, okay? Take care, bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.